Welcome back to Boiler Wild. My name is Eric Johnson. On this podcast, talk about boiler industry topics as well as personal development. I got a very simple podcast for you today, but first I want to thank you for listening. If you are tuning into this podcast, thank you. This one will be a boiler topic. So hopefully you learn something. If you are newer, if you are very experienced, this will probably be a review for you on this topic, but I never know because this topic came up from a Facebook post on a boiler Facebook page for stationary engineers, and theoretically stationary engineers are licensed and should be knowledgeable on boiler operation and steam systems. Quick note, if you haven't already, please rate the podcast 5 stars on your podcast app. That would really help me. I do this podcast for free for love of the game to try to help you. I appreciate the couple of messages people have sent saying how much they love the podcast or have comments about a specific episode. But just rating the podcast helps other people find it. And also, if you work with somebody that would like to listen to the podcast, please share it with them. So today we're going to talk about siphon loops and what they are, their purpose, a little bit of history, and requirements. First of all, I want to say siphon loop. That is the most correct term for what I call this piece of pipe, and a common industry term, nickname, is called a pigtail. If you ever drew pigs as a kid, you would draw the tail with a little squiggle, with a circular squiggle. Kind of looks like a curly fry, but it only has one loop in it. So what is a siphon loop? A siphon loop is a piece of pipe, and they can either be straight siphon loops or they can be 90-degree siphon loops. And it's a piece of pipe. So think in your mind, you have a piece of pipe. Let's say it's going in the right-hand direction. So we're going to head towards 3 o'clock on the clock. So it's a piece of pipe heading towards 3 o'clock, and then it's going to do a full 360 and then keep heading towards 3 o'clock. So it's going to be a full loop in the pipe. Typically, the siphon loops are going to either be a 1/4 inch, that's the most popular size, or they can be 1/2 inch for some larger controls. That is more rare. Typically, you're going to find 1/4 inch. You can also find 90-degree siphon loops. So if we're looking at a clock again, we would be heading towards 3 o'clock. Then you would do a full 360, but then you would keep going another 90 degrees, and you'd be heading towards 6 o'clock. So that would make a 90-degree siphon loop. Those are used less than the straight siphon loops, and there's all kinds of different manufacturers of straight siphon loops on how they actually bend the pipe. But the siphon loop is typically probably 6 inches long total. It is just a piece of pipe that is bent, and it's going to be threaded with national pipe thread on both sides. Like I said, typically the size is going to be 1/4 inch because most pressure controls on a steam boiler are going to be 1/4 inch connection on the pressure control. I want to talk about what the purpose of a siphon loop is in relation to pressure controls. And I saw this post on Facebook in the Stationary Engineers group. And one, this is not a dig at the poster. It takes a lot to post a question on the internet. So that is good that they are posting the question that other people don't know. But it's also, while groups like Facebook and Reddit are great to get a variety of answers, you will probably get a variety of wrong answers, which is concerning for how simple the question is and for a group with supposedly licensed stationary engineers in it, how much of a variety of answers that were answered to this question. So I will read the question. What do we call the pipe that all the pressure controls are mounted to? That is typically called a control manifold, steam pressure control manifold, control tree, header manifold for pressure controls. It is a pipe that will have one connection to the boiler, but then multiple connections of pressure controls along the pipe. That will vary boiler by boiler, but that is typically what is done on Scotch Marine boilers. Some boilers just directly connect each pressure control directly to the steam space of the boiler. Like if you have a cast iron boiler, that can happen sometimes, or if you have a firebox boiler, that can happen sometimes. There's no right way or wrong way. It just depends on how it's done. Water tube boilers, they can vary on how they connect the steam pressure controls. But for a high pressure boiler, high pressure steam boiler, so that's going to be anything 15 psi or over. But for a high pressure steam boiler, so that's going to be any boiler over 15 psi, it is going to have multiple pressure controls on the control tree. And I like to call it a control tree. You can call it whatever you want. I don't think it's really defined anywhere. I haven't seen a definition that is like, it has to be this. Varies. Maybe the steam pressure control manifold is the most correct, but I like to call it a control tree. You are going to have your operating control, which is going to be what is going to shut off the boiler on and off. Then you're going to have your high pressure limit, which is typically going to have a manual reset. And then you will typically also have a modulation control or a pressure transducer. So that is just 3 examples of controls. You can also have like a day-night control for steam pressure if you want to lower the steam pressure at night. It's endless, the amount of controls that you can put on, but typically you'll have 3 connections on the control tree. Going back to the question, is it supposed to be filled with condensate or steam as the pipe stays cool, but it comes off the steam line connected to the low water cutoff? So if you imagine a Scotch Marine boiler, so we're going to do a horizontal fire tube boiler. The low water cutoff connection comes off the top 12 o'clock of the shell, and the pipe comes up a little bit with typically a short nipple, and then it goes into a cross, and then it goes directly either way, depending on which side is connected. So we're going to say it goes to the right. So it goes towards 3 o'clock, and the pipe will come over, and then another tap into the shell will come off at the 3 o'clock location on the shell, which is typically about midway on the shell, the 50% mark. And you will have another cross there, and then it will run up on the connection. You will have a low water cutoff, and then it'll connect to the top with another cross. So the 12 o'clock position of the shell and the 3 o'clock position of the shell of the boiler are going to be the 2 connections of the low water cutoff. And on the pipe that is in the horizontal in the steam space, so if you think about where the water is going to be in the boiler, let's say it's about 75% full in the shell, you are only going to have water. Water's going to find its own level. You're only going to have water in about 2/3 of the pipe that's on the vertical coming off the 3 o'clock position on the shell. That is where you're going to find typically your low water cutoff, which is like a McDonnell Miller 150 control. And that's where your water level is going to sit. Anything above that water level is going to be your steam space. So on the horizontal pipe, that connects the cross at the 12 o'clock position, and then connects the cross for the vertical coming up from your low water cutoff from the 3 o'clock position. You can have a connection for your control tree or your steam pressure control manifold. That connection can go in towards the 6 o'clock. So it's going to go directly straight down, and then it's going to branch out from there, and you can connect all of your controls, but it's only the controls are only going to be connected to one spot, to the steam space of the boiler, which is going to be a T or a cross off of that horizontal pipe. I hope that makes sense. This is a little bit easier to describe with a drawing, but this is a podcast, so no drawings today. Going back to the properties of steam, we need to remember that water is not going to turn to steam by itself. We have to add heat to the water. It has to become 212 degrees, and then we have to keep adding 970 BTUs per pound of water in order to turn that 212 degree water into steam. Now that steam, once it's made, it's going to exit the boiler and travel through pipes. If we stop heating the steam, which we typically do once it leaves the boiler, if we stop heating the steam, it now wants to return back to water because it is losing heat. So as the steam loses heat, it gives off radiant heat. The pipes are hot. Let's say we didn't insulate our pipes, so we're losing 20% off the pipes, and then it goes through a coil, a steam heating coil, and we have a fan over the coil, and it's turning that steam heat into hot air. At the bottom of that coil, you're going to see a steam trap. That steam trap keeps the steam in the coil, but it allows the condensate to come out of the coil. Condensate is produced because the steam loses enough heat energy and will turn back into the liquid phase, which we call condensate. That condensate then goes through the steam trap and can get sent back to the boiler. Going back to the control tree, if we have a control tree and a piping configuration where there is only one connection to the steam space, we have no flow through the control tree. You should not have flow through the control tree. It should not be like a loop like you would have on your steam system. It is just one connection to the steam space, like I talked about previously on the horizontal pipe. There typically is a drop down on a Scotch Marine boiler. We're just talking about Scotch Marine boilers here. That is the only connection. Sometimes people will put a valve and put a blowdown line connection. That is only for draining the control tree because the control tree will fill up with water. Why does it fill up with water? So we took apart a boiler. We took all the piping apart, put it all back together. The boiler is completely empty. We fill the boiler with water. Now we fire the boiler and we put it in low fire to warm it up slowly. We start making a little bit of steam. That steam is going to start displacing the air in the steam space of the boiler. Remember, the boiler and the steam piping isn't empty. There's actually air in there. We like to think it's empty because we think of atmosphere as empty, but air actually takes up space. Air is something. So you start boiling the water inside of the vessel. The steam starts displacing the air in the boiler and will start traveling everywhere it can. One of the places it will travel is to the control tree. It will go up into the top of the steam piping that is off the 12 o'clock position of the shell. And that connection to the top of the shell is used as the equalizing line for that low water cutoff that I described previously. But the steam will travel, and it will travel down into the control manifold. And now it gets stuck in the control manifold. We are not heating the control manifold. There's no heat added to the control manifold. Typically, they're going to be uninsulated, so they are going to lose heat. The piping is going to lose heat pretty quickly. And once we know that steam will want to turn back into condensate or water, once it loses enough heat, we'll understand why the control tree fills up with water. So the steam goes into the control tree, displacing the air, and once it loses enough heat, it turns to water. Since the control tree has no flow in it, it is going to slowly fill up with water. This is not an issue because you also know that water or a liquid cannot be compressed. This is how hydraulics work for like construction equipment or like a forklift. You have a hydraulic pump and it pushes fluid and pushes force through fluid. So the pump puts force on one side of the pipe of the fluid, and then 10 feet away, that force is seen coming from a cylinder. That force is being directly transferred because you cannot compress the liquid. If you were to use compressed air instead of a hydraulic system, air can be compressed. So it'd be like using a spring, and it'd be very, very spongy, and you would never really get accurate control of, say, an excavator arm if you were going to be using compressed air or even steam, because a gas can be compressed. A fluid cannot be compressed. So your control tree fills up with water, which is fine. And now the boiler is roaring. It's making 100 psi of steam. That steam is still going to be up in the top steam equalizing pipe that eventually comes off the 12 o'clock position of the shell and then will travel horizontally and get connected to a cross that then goes down to the low water cutoff, and then that gets connected to the 3 o'clock position on the shell, which is going to be for your water connection for the low water cutoff sensing line. That steam in the top connection is going to push in all directions. Gases will push in all directions, and they will fill up the container that they are allowed to fill. And that steam, while it is not traveling down anymore into the control tree, is going to be pushing on the water that is filling the control tree. That force on the water that is pushing at the entrance of the control tree that is on the drop coming off the horizontal pipe, that force is going to be directly transferred to all of the pressure switches that are connected on the control tree, because we know, as I just explained, that water or liquids do not compress. So if we were to add 100 psi of force, and that's pounds per square inch. So if we had a 1 inch by 1 inch pipe, and 1 inch pipe isn't exactly 1 inch by 1 inch, but if we had a 1 inch by 1 inch pipe, that would be 100 psi of force. That same amount of force is going to be transferred to all of the pressure controls, and it doesn't split. So a lot of people will think, well, the force is going to be split by 3 if we have 3 pressure controls. No, it's going to always be equal. So if you have a force of 100 psi on the entrance of the control tree, you're going to have 100 psi to the bottom of the diaphragms of each pressure control on the control tree. Going back to the question, I asked both of the 2 engineers I'm working with, and one states it's supposed to be filled with condensate and be cool, and the other states it's supposed to be hot. The control tree is going to be ambient temperature. It will probably feel hot to touch, but it will not be steam pressure hot, like if you were going to touch the steam line of the boiler. But since the boiler is going to be radiating heat, other parts of the room are going to be radiating heat, the line is going to be warm. I'm not going to say it's going to be cold. It's going to be warm to touch, but it will not be steam hot to touch. So if you had a 100 psi set point and you had a 100 psi on the boiler, 100 psi is whatever temperature. Let's just say it's 300. That's wrong, but I don't know my steam temperatures off the top of my head. 100 psi is going to be 300 degrees. That pipe would be 300 degrees. if you were to touch it. And it's not going to be 300 degrees because it is filled with water. The water does not transfer the temperature of the steam. So it is going to be warm to touch. It may be a little warm. You may want to wear a glove, but it will typically just be ambient temperature. Since there's no extra heat that's getting added to the control tree, any water inside is just going to pick up the ambient temperature that is around it. Going back to the question, this is the question writer. My assumption is that it should be hot since it's a steam space pressure, but my confusion is there's no pigtails, so wouldn't the controllers be damaged by hot steam? And also, if it's not supposed to hold condensate, why wouldn't it have a steam trap? All right, so the first part of that, since it's connected to the steam space, so I already answered that, but we'll go back over it. So it's connected to the steam space, but the control tree or the control header manifold it only has one inlet. There's no outlet. So since there's no flow, the steam gets trapped inside the manifold. The steam will cool, it will condense into condensate, and the manifold will fill up with water. So just because piping is connected to the steam space doesn't mean there's going to be steam in it. You're only going to have steam in it if it can flow out. If you were to take the plug out of the pipe out of one end of the manifold, you would have a little bit of water coming out, and then you would have steam coming out. That is obviously going to be bad. You do not want flow in your control tree manifold. That flow is bad. Any flow, there should be no flow. There should be no active blowdown lines that you're blowing down all the time. All the control tree manifold is to sense the steam pressure of the boiler, and having water in it, as I just described, does not prohibit the pressure controls from sensing the steam pressure. And then the second part of that, since there's no pigtails, when the controllers be damaged by hot steam. The whole point of a pigtail is to trap a little bit of water. Well, let me back up. I haven't read the initial lore when the dark magic of pigtails was written. I haven't gone that far in history. There can be two uses for a pigtail. In modern controls, typically only one is used anymore, but I will describe both. The first major use is to trap water and have a water seal to protect the pressure control from the temperature of steam. So they could make a pressure control that stands up to the temperature of steam, but it would be very expensive versus just having a pressure control that can stand up to the temperature of the water that is going to be picking up the ambient and then stand up to just pressure. So 100 psi of air pressure is much different than 100 psi of steam pressure. Pressure is pressure, so on a pressure gauge, they will read the same, but measuring it, the air does not have latent heat. The steam, what makes steam magic is the latent heat of steam. And when we talked about boiling water, so we're boiling water, a lot of people say, well, when you get water to 212, it's going to turn into steam. That is actually false. Water can be 212, and then you have to keep adding 970 BTUs to it per pound, and then it will turn into steam. And that 970 BTUs is what makes the magic of steam. That is called latent heat. That is the phase change that happens. You go from a liquid to a gas. One of the laws of thermodynamics is energy is neither created or destroyed. So we've added 970 BTUs per pound to make that into steam. That energy doesn't just go away. That travels with the steam, and then that steam releases that energy, and then as it condenses, that energy is released, and that is why steam is so effective as a heating substance and has not been replaced. One, because water is of basically infinite quantity. It's everywhere in the world. But 2, the properties of steam and water are very well studied and always understood, and they're the same. You don't mix up water like you would mix up like oil. Chemical manufacturers can mix up oils to be different properties, have this, have that, but water is always the same. Steam is always the same. Steam at 100 psi, as long as it's saturated steam and not superheated steam, saturated steam at 100 psi is always going to be the same temperature no matter what. So going back to the question, wouldn't the controllers be damaged by hot steam? So in this question, the control tree is as I described it. The connection comes off the top horizontal pipe of the equalizing line that goes to the low water cutoff. It comes down and then it's just nipples with T's, and those nipples go into the pressure controls as well. There are no pigtails. That works because the entire control tree acts as a water seal. Instead of having an individual pigtail for each pressure control as a water seal, the entire control manifold is a water seal. Therefore, each control would be protected from the hot steam. That hot steam, what we're really talking about is that latent heat of that steam. And then the second part of that question, and also if it's not supposed to hold condensate, why wouldn't it have a steam trap? Kind of confused on this. This doesn't even make sense if you know boilers. So steam traps are only supposed to hold back steam for loads or low spots in systems. So if everywhere you have a low spot where there's going to get water, you need a steam trap. If you were just to put a drain to drain out the water, steam is just going to travel out the drain because the steam is going to be traveling down the pipe, and then you come to a turn, which is the low spot. It's just going to travel right out the drain. It's going to go to the path of least resistance. But since you have a steam trap, that steam trap will push back all the force of the steam into the system, so the steam doesn't see that steam trap. But since there is a dead spot or a low spot, and the steam is always going to be wanting to turn into water, water is going to collect into that low spot, and a steam trap is designed to trap steam but pass condensate through. So to have a steam trap on a control tree, one, it just doesn't make sense if you know what a steam trap is and a control tree is. 2, it's illegal, but I don't even know how to explain that because it just doesn't make sense. So there were 228 comments on this, and the comments were a mix of, I'm not sure, but looks like a code violation. So a lot of them said you need to have pigtails. Well, they didn't seem to understand that the entire control tree manifold is taking up the purpose of a pigtail, which is providing a water seal between the steam pressure control and the hot steam. If you connect your control tree to the steam space, but it is piped so that let's say if you had the horizontal that comes off the 12 o'clock position of the shell, you had that horizontal pipe that then would take a 90-degree down and go into your low water cutoff that then keeps going down and then takes another 90 back into your shell at the 3 o'clock position. Say you came off that horizontal pipe that was in the steam space and you went directly up and then you made your control manifold. That control manifold would naturally drain because it is in the up position from the steam space, and any steam that traveled up into the control manifold or the control tree, once it condensed, that condensate would, by gravity, drop back down into the horizontal pipe and then either go back into the shell of the boiler or go back into the low water cutoff. In that case, you would need a pigtail at the bottom connection of each pressure control because the manifold, the control tree, is not providing a water seal for the steam controls. So in that case, you would need a siphon loop or pigtail. But Eric, pigtails are required by code. Well, one, if somebody says it's a code violation, they need to recite the code 95% of the time. And I think it's probably higher than that, but that's a made up percentage. 95% of the time, when people say that's code or that's a code violation, they don't actually know what code or what code they're violating. They have just been told it's a code violation and they've never looked it up. So let's go to CSD1. We are section CW 310 of the 2024 CSD1. And CSD1, if you are unfamiliar, governs automatic boilers from 400,000 BTUs to 12.5 million BTUs. That's the scope. And it only applies to boilers, not water heaters. But the 2024 CSD1, section CW 310, requirements for pressure controls for steam boilers. Section F, each pressure control device shall be protected with a siphon. Oh, it says right there. Every siphons are required for CSD1. Well, the next word comes into play and is very important. And if you are any part of English major or understand English and sentence structure, this is very important. Each pressure control device shall be protected with a siphon or equivalent means of maintaining a water seal that will prevent steam from entering the control. The minimum size of a siphon shall be NPS 1/4, so just 1/4 inch, and it goes on about tubing and substitute piping, whatever. But going back to that, each pressure control device shall be protected with a siphon or equivalent means of maintaining a water seal. So you have an either or. So we have a binary decision. We have a steam boiler. We have pressure controls. We have to protect the pressure controls from the temperature of the steam. How are we going to do that? We either need a siphon loop on each pressure control or an equivalent means of maintaining a water seal. And that water seal is what I call like a drop-down header or a drop-down control tree. And it's any control tree that is lower than the position it connects to, which is the original control tree that I was describing. You have that horizontal pipe that then comes off the 12 o'clock position of the shell and then goes over to the low water cutoff. That horizontal pipe, you have a connection to it and it drops down. And since we know that control trees do not have flow through them, the steam gets trapped and that entire section of piping becomes trapped with water and will fill with water. And since water or in liquids cannot be compressed, all the pressure of the steam is transferred through that water equally to each pressure control. And that is how that works. If we have a control tree that does not trap water and water is going to drain out of it, we need a siphon loop in order to provide a water seal directly under each pressure control in order to keep the heat of the steam from touching the diaphragm of the pressure control. And then you say, well, Eric, I've seen drop headers or drop control trees with siphon loops. And I would say that that is unnecessary and almost probably bad unless you have mercury switches. So back in the good old days, we used mercury in pressure controls. The most common one, I think the only one that I know about really, is the Honeywell Pressure Troll. Pressure Troll is a trademark name, just like tissue and Kleenex. Tissue is the common name. Kleenex is the trademark name. Pressure Troll is the Honeywell trademark name. But since Honeywell, for some reason, was like the steam control maker forever, Pressure Troll became a common industry name for the steam pressure controls. So going back to CSD1, when a control incorporating, this is still section F. When a control incorporating a mercury switch is mounted on the siphon loop, the loop of the siphon shall be in a plane that is 90 degrees from the plane of the mercury switch. So going back to the good old days, and you can't buy them anymore. They don't make switches with mercury unless you buy them on the aftermarket, like used, like eBay. You can still find brand new switches, but they're going to be like, hey, I found this switch on the shelf of an old power plant. It's brand new in the box. I have a couple mercury switches myself, but mercury switches, they rely on being correctly orientated to the horizon. And by horizon, I mean 90 degrees or perpendicular to gravity. So gravity, in theory, if you think about it, is pulling straight down towards the earth. The horizon, and this is going to be how water levels, is going to be 90 degrees to gravity with no other forces on it. And that's how you get like the water level in a glass. A mercury switch has to be level, and in order to indicate that, there is a pendulum arm, almost kind of like what you would see on like an old school grandfather clock. But there's a little pendulum arm, and by pendulum arm, I mean a little 3-inch sheet metal stamped indicator inside of the control with a little point at the end. And that point has to point at a mark on the back of the control. And that will tell you that the control is in the correct vertical position, as in the control is correctly mounted so that the pendulum is at that mark and that the mercury switch is going to work correctly based on the scale. The switch will work if you were to tip it a little bit one way or the other, but it would completely throw off the scale of the switch. And if the switch were to trip at 100 psi, and if you were to tip the switch one way or the other, it would no longer trip at 100 psi. That is one of the downsides of using a mercury switch. So we also know that when piping heats up, it moves, and a siphon loop is a straight siphon loop is typically a 1/4-inch piece of pipe, and then you have a loop, and then the straight comes out the other side of the loop. If we heat that up, it is going to bend that loop a little bit. And as I talked about just previously, mercury switches need to be correctly orientated, but it only matters if you're looking directly at the face of the switch, which is going to be the clear cover of the Honeywell pressure control. And you're going to see the scale on the left-hand side, and you're going to see the mercury bulb on the top right side, and then the electrical connections below it. If you're looking directly at the switch, it only matters if it is tilting towards the right hand or left hand. It doesn't matter if it's tilting towards you or away from you. So going back to CSD1, when a control incorporating a mercury switch is mounted on the siphon, the loop of the siphon shall be in a plane that is 90 degrees from the plane of the mercury switch. So the mercury switch, you're staring at it. It's directly staring right at you, and you have your right hand on your right hand side and your left hand side, and you're holding them out, your arms directly out on either side of you. If you were to tilt one way or the other towards your right hand or your left hand, that switch is going to get thrown off on what pressure it actually trips at. But if you were to take a step towards the mercury switch or take a step away from the mercury switch, that movement does not affect the mercury switch, as long as it's a little bit. I'm sure if you laid down the mercury switch, it probably wouldn't work correctly. It may still trip, may not. I'll have to test that out. But the plane of the siphon, so think about a loop. If you were to put it parallel with the mercury switch, so you have your arms out to either side of you, and the loop is parallel, So think about drawing a circle on your chest. That would be a parallel loop to the mercury switch. When you heat that up, you are now going to be either tilting your arm to the right or to the left, and that is going to throw off the mercury switch. You need to mount the mercury switch in a plane that is 90 degrees. So think about drawing a circle through your chest. So that's going to be 90 degrees to the plane. So from your sternum or your chest to your back, if you have your loop that is 90 degrees of the mercury switch, when it heats up, you're going to either be tilting towards the mercury switch forward, so you're going to be taking a step forward, or you're going to be taking a step back from the mercury switch. But that movement of position does not affect the set point change of the mercury switch, and therefore the purpose of the siphon loop is to keep the mercury switch in the correct horizontal position to the horizon. But now, in modern switches, we have micro snap switches, and they don't care how the switch is mounted, since it uses a spring pressure and all that, and not uses mercury, which is a liquid. So instead of using a liquid, which relies on gravity, the snap springs and snap switches inside the switches don't really care about gravity. So now it doesn't matter how you mount the pressure controls, and people who don't know better or just repeat what they've been told will see modern pressure controls with snap switches with the siphon loops that are mounted parallel to the right or left of the switch. So drawing a circle on your chest with your arms out to your side, on either side, pointing out in each direction. If the switch were to tilt one way or the other on a modern snap switch, it wouldn't matter. But they see that and then they say, oh, that's wrong. It needs to be turned 90 degrees so that the circle would be drawn from your chest to your back. So 90 degrees of your arms pointed out in either direction. Yes, it is good practice to do that, but it doesn't matter when you have a modern snap switch. That is old school knowledge of mercury switches transferring over to modern switches that do not have mercury. In reality, it doesn't matter if you are installing siphon loops on switches. You can put them in the 90 degree position so that the loop is 90 degrees of the right to left, but it doesn't matter. But good practice is to put it in the 90 degree position, mostly to keep ignorant people and inspectors from telling you it's wrong and that you need to change it. But it really doesn't matter. That knowledge is only for mercury switches. Some places, and by places I mean jurisdictions, require siphon loops no matter what. And if you explain that the control manifold is the siphon loop and provides the water seal and is the same thing, and adding siphons is redundant and actually a little bit more dangerous because now the siphons are less likely to be taken off individually and will plug up. Good luck explaining that to an inspector. But some places want to see siphon loops on steam pressure switches no matter what. So you just have to install them. But if you have a drop control tree, as in a control tree that will trap water, you do not need siphon loops because the trapped water replaces the purpose of the siphon loop to provide the water seal. Also, going through the comments on this, the 228 comments on this post, here's another one. Each of those controls should be on its own pigtail, whether the header has some sort of siphon on it or not. So that is false, as from the information I just told you. It is a control line. It should never be hot. Steam condenses and the line is filled with condensate. You should never drain this line. When you have steam, steam will damage the switches and you will be buying new ones. So that is correct. Although I will say, if you drain the line while the boiler's online, like if you do have a drain, it doesn't automatically just cook the switches. It's the time and temperature. Steam initially touches the switch when you start up the boiler, but it's so little amount before it becomes water that it's really a non-issue. Theoretically, if you were going to be perfect, you would fill the control tree piping with water before you started the boiler. But if you had siphon loops, you would fill them with water before installing them on the piping and then installing the pressure controls. Some people do that, some don't. It really doesn't make a difference because the steam will enter that siphon loop and almost immediately condense the water and then provide a water seal. If you were to connect a steam pressure control directly to steam and have no water seal, it wouldn't just immediately fry itself. It would work, but then it would eventually not work. The switch is not rated for that, but if steam touches it, they don't just like melt and stop working. So most of the comments were correct in answering some or all of the poster's question. Some were incorrect of saying, hey, where are the pigtails? You need pigtails. Pressure controls have to have pigtails. Typically, people who say that don't actually know why or the purpose of the pigtail, or they think and have learned on mercury switches only and have not cracked open a book or a manual in the last 20 years. Here's another one. Mine's done like that, and the best thing to do is just put a drain valve on the end of it. Ever so often crack the valve, let the water out. I do mine once a week. And then the poster replied, and then the same guy replied again that made that first comment. Well, they need to see the pressure, not get the high temp steam, and as long as you don't leave the valve open for more than a second, it's fine. I just barely opened mine long enough to drain the water. Haven't had to change pressure controls for a while, so it must be fine. So sometimes people will add drain valves to the control tree. This is fine as long as you understand that you should never open the valve when the boiler has steam pressure on it. You never want flow on your control tree or your control manifold on your steam pressure controls. Water inside of the piping does not prevent pressure from getting to the steam pressure controls, as this commenter indicated, and draining the condensate will drain the condensate out of the piping for about 2 minutes, and then it'll be full again. Not even 2 minutes if your boiler's running. So one, don't drain it if you do have a drain valve on it. Typically, a drain valve is used for shutdowns to drain the water out of it without just dumping the water. When you take the T out of the, or you take the plug out of the end of the T on one side of the manifold to inspect it or to clean it out. You can also use it as a point to verify that you have no pressure on the boiler. Opening a valve that can be quickly closed again and seeing if there's any steam coming out is much different than taking a plug out and then having still like a pound of steam pressure on the boiler. A pound of steam doesn't seem like a lot, but it will definitely burn you if you put your hand in it. All right, so most of the comments were correct. Some were incorrect, but I worry about people who are stationary engineers who don't know the specifics. And as a stationary engineer, as a service technician, as somebody, as even an engineer, a licensed engineer, as somebody who works in an industry, you should always want to learn. However, that's not the case, but that's the whole point of this podcast, to encourage education and learning. And if you are listening to this, I applaud you, and I also appreciate you because you are taking the time to learn, and hopefully I am able to teach you something. So that is the point of a siphon loop, trade name Pigtail. They come in straight or they're in 90. They also come in iron and brass. I won't get into the iron and brass talk now, but CSE1 says one thing and then some jurisdictions say some other things, and there's a lot of people who don't read the sentence structure of CSD1 or of the National Board Code, which also mentions it. But just be mindful that your jurisdiction may require you to have brass or non-ferrous siphon loops. Those are actually better probably than steel. You just need to make sure that they are rated for the pressure of the boiler, and they need to be rated for the MAWP of the boiler at a minimum. I don't know like the actual, but if you were to have a 150 psi boiler, but you only run 50 psi, getting siphon loops that are good for 50 psi is no bueno, because every connection or every part on the boiler that is exposed to the pressure side of the boiler needs to be rated for the pressure of the boiler. You cannot, unless it's limited somehow, because somebody may say, hey, I'm going to buy this boiler, and then they crank up the pressure to 120 psi because it's a 150 psi boiler and the safety valves are set at 150 psi. But now your siphon loops are only meant to hold 50 psi, so that's an issue. So it always needs to be at minimum the MAWP of the boiler. But that's a conversation for another day. Just be mindful of it. But that is the origin of siphon loops. They provide a water seal for steam pressure controls, and they also help maintain proper orientation on mercury switches. Modern snap switches for pressure controls do not care on their orientation. They need to be installed in the vertical orientation. It's probably in the manual, like the Honeywell pressure control manual. But if it's tilted a little to the right or to the left, it doesn't really matter. On mercury, it matters because that will change at what pressure the switch will actuate, because mercury is a liquid and moves around, and it needs to be referenced to the horizon. Thank you for listening. I hope you learned something. You probably never thought that somebody could talk about pigtails and siphon loops for an hour, but here we go. 1 hour down on pigtails. You are now educated. Share this episode with somebody. And also, if you're a service technician, educate your customers. You can now talk about it, hopefully correctly, but talk about siphon loops and why they're there or why they're not there, and why a drop control tree provides the water seal and you don't need siphon loops. So thank you for listening. I appreciate you all, and stay wild.